next up we have learning quadruped locomotion using differentiable simulation, and we have Yun Non Song talking about it.
Check. Okay. Good afternoon, and my name is Yun Non, and I just finished my PhD at the Robotics and Perception Group at the University of Zurich. And today, I would like to present our work on learning quadruped locomotion using differentiable simulation. And this work is also done in collaboration with Professor Sambae Kim from MIT. So, throughout the history, the problem of quadruped locomotion control has started from simple template models and combined with cascaded control design. And this representation, template representations, is very simple, like slip models, but they are very effective. And later, optimal control methods was used to solve more complex problems. And the main advantage of optimal control is that you can formulate very complex optimization problem and use more complex models within one optimization framework. It has achieved impressive result in controlling different types of robots, such as the post-dynamic sport and also MIT Mini Cheetah. And since 2019, 2017, reinforcement learning has been the core approach that drives the research in quadruped locomotion, especially going beyond lab environment, going into the wild, like locomotion over challenging terrains. It seems like reinforcement learning is the final answer, especially nowadays given the open source of many codes. Bachelor students can easily train a very powerful reinforcement controller for solving very complex locomotion problems. However, when it comes to more complex problems like vision-based inputs, reinforcement learning alone is insufficient. It is generally nowadays we see many presentations, many work that combine reinforcement learning with imitation learning in order to solve vision-based navigation tasks. And the fundamental reason that we still need imitation learning as the second stage of the training is because reinforcement learning is simply inefficient. And this limitation motivates this work. And we aim to answer this question: can we speed up policy optimization? So we can take inspiration from another approach, optimal control. Optimal control is very simple, efficient, in a sense that it solves the optimization problem very efficiently. And the reason is that it uses the models to compute the gradient. On the other hand, reinforcement learning does not use the model to compute the gradient. It simply does samples and then compute the policy gradient using sample data. So the key idea of our approach is to do policy optimization using analytic gradient. This is very general formulation of policy optimization. So you have a loss function, which is a function of the state and also action. And you want to minimize this loss function using stochastic gradient descent. And the key is how can we compute the gradient. So you can expand this equation and you can get the analytic gradient. So the key component in this equation is this modification of the system dynamic Jacobians, which indicates that we need to backpropagate the gradient through the dynamics as well as through the time. And so how can we compute this analytic gradient? And this is done through differentiable simulation. The main idea about differentiable simulation is that you start from some some state, and then given this state there's observation, and then you compute the action given observation and do forward propagation to roll out the trajectory. But for the optimization of the policy, you do backpropagation by backpropagating through the dynamics of your robot. It sounds simple, but it is very difficult. For instance, it requires the model to be differentiable. The objective function need to be differentiable. And in most cases, like quadruped locomotion, the dynamics is discontinuous due to the contact. And the key idea of our approach for handling discontinuous dynamics is to use surrogate gradients. Meaning, when you do forward propagation, you can use any models. This model can be black box. You can use even the real-world models. But for backward propagation, you use a simple surrogate model to compute the gradient. And this surrogate model provides better gradients. And for instance, for the quadruped locomotion, we can use the Isaac gene as a black box simulator. But for backward propagation, we can use simple single rigid body dynamics, which is continuous representation of the robot bodies. And there's an additional step because two models are different. So when you roll out the trajectory, eventually they diverge. So you need to align the state in order to make sure that the state of the robot is still grounded by the true physics. And we apply this approach to the quadruped locomotion problem, and the task is very simple here. We define a task such that the robot is required to move forward. And we only simulate one robot without any parallelization. And after roughly minutes, like 10 minutes of training with only one robot, the robot managed to walk. But we can still leverage the power of GPU, like we can still parallelize the robot. And in this task, we design a task for learning diverse locomotion skills on challenging terrains. And the skills include different gait patterns, such as pace, charge, bound, and gallop. And they work on different terrains. And we do not parallelize massively, like thousands of robots, but only 64 robots, but still it managed to learn very quickly. And here's a comparison between DiffSim and PPO, and the blue line indicates the DiffSim, and the other one indicates the PPO. We see when parallelized 64 robot, DiffSim converge much faster. When you scale the robot up to thousands, both still manage to solve the task, but DiffSim is much faster. In terms of computation time, both approach manage to solve the problem within very similar time. We also deploy this policy in the physical world, and to my knowledge, this is the first successful sim-to-real deployment of quadruped locomotion using differentiable simulation. And the performance in terms of robustness is still not as good as PPO, but still it can be deployed to the real world. We also have some additional result on quadro rotor control, and here you see my colleague Johannes. He has a drone, hold it on his hand, and he throws the drone, and the drone needs to hover, given observations purely from those dot points. And those dot points represent visual feature observations. So the drone doesn't know the true state of the robot. And in this case, it managed to solve the task very efficiently. So given the full state, it takes only seconds to solve, but when we remove the state assumption, for vision-based, it takes minutes to solve. If you want to know more, you can reach out to Johannes on Saturday in the workshop. So in conclusion, policy optimization via analytic gradients greatly improve sample efficiency compared to reinforcement learning, and surrogate models allows for efficient policy training as well as sim-to-real transfer. And vision-based end-to-end control, I believe it can benefit more from differentiable simulation. Thank you.
Wonderful. Do we have questions? Yes.
Hello, thanks for the talk. I was wondering, did you compare your method with learn dynamic models like Dreamer that also do policy gradient and learn the dynamic as well? So if you do, what are the differences?
So we didn't do this study, but for Dreamers or model-based IL in general, the main difficulty is learning the model itself. And if you would apply Dreamer, most of the time used for learning the model itself. Actually, learning the policy is very easy once you have a good models. So I think the challenge there is learning a good models. And we do not learn, we just directly use the analytic models.
We have other questions. We have one here. We have one. Please go ahead.
Thank you for the talk. Yeah, that's a very good one. But I have a question. So, do you need predefined stepping patterns for the quadruped robot?
Yes.
Okay. Do you? Okay, cool.
All right. Thank you very much for the great talk. How do you think you can? Oh, this is a question. How do you think you can extend this kind of idea of a surrogate model to more complex tasks where you don't have rigid body dynamics?
For instance,
I don't know, soft terrain.
I haven't really thought about this question, but the key idea is that you can still combine a surrogate model for gradient, right? As long as you can find such models, a simple one, like for any problems that you have, you can still combine with the true models, like the state alignment. So I think it will be very interesting to see how it performs, but I didn't really do this kind of studies myself.
And I have a question myself. Did you compare with analytic differentiable simulators, getting the gradient directly from the simulator rather than creating this two-model system?
Yes, in the second one, like the quadruped control, because there we have the true model of the quadrupeds, we did comparison. So both, like using surrogate model and using the directly the analytic models arrives the same performance, but using simpler surrogate models basically allows much faster training and also efficient training.
Wonderful. Let's thank the speaker once again.